Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we are undertaking, well, a really critical mission, I think. We're trying to find the true measure of efficiency. And that means kind of challenging the limits of something fundamental, the first law of thermodynamics.
Yeah, absolutely. Every engineer, starts with the first law.
Yeah.
And you have to. It's basically the universe's accountant. It makes sure energy quantity, the amount, is conserved, tells you what you started with, what you ended with. No energy just vanishes.
But, I've always felt the first law was maybe a bit simplistic. Like, okay, energy is conserved. Great. But you could have a whole system full of conserved energy that's completely useless for doing actual work, right?
Yeah.
If it's all just spread out, low quality, ambient temperature stuff, it feels like it ignores the quality aspect.
That is the core problem, and that's where the second law steps in. It's the quality control officer, if you will. Now, traditionally, we look at this through the lens of entropy. Entropy tells us, which way processes naturally go, and crucially, how much energy must be rejected. You can't convert it all.
Right. Entropy is fundamental, absolutely. But you mentioned we're focusing on a different property today, one that gets more directly to the practical bottom line. We're talking about availability, sometimes called exergy.
Precisely. Availability is engineered specifically to answer the question, what is the absolute maximum useful work a system can perform as it comes into equilibrium with its surroundings? Our mission today is to accept that the second law forces some energy rejection, always, and then find the shortcut to calculating the theoretical maximum work we can actually extract despite that.
Okay, let's dive in. So, defining useful work seems like the first step.
It is. Let's think about a system doing work, maybe expanding gas in a piston. The total work the system does, let's call it delta W sys. But when that piston moves, not all of that work is doing what you actually want it to do.
Ah, okay. So if I'm using the piston to, say, lift a weight or turn a shaft, that's the useful work. Let's call it delta WU. But the piston itself, just to move, has to push the air around it out of the way. The atmosphere resists it.
Exactly. That's the displacement work done against the environment, delta W sur. And if the environment's pressure is constant, say P naught, ambient pressure, then that work is simply P naught times dV, the change in volume.
Okay, so the useful work I get out, delta WU, is the total work the system generates, delta W says, minus this work wasted just pushing the atmosphere around, delta W sur, or P naught dV. It's like an unavoidable tax you paid to the environment just for existing and changing volume.
A perfect way to put it, an environmental tax. And this unavoidable interaction with the environment leads us straight to the next key idea, the dead state.
The dead state. Sounds a bit grim. Why that name?
Well, it's maybe a bit dramatic, but it's conceptually our 0 point. The dead state is where your system is in complete thermal and mechanical equilibrium with its surroundings. It's at the same temperature, T naught, and the same pressure, P naught, as the environment. At this point, it's done. It's thermodynamically retired, you could say. It has absolutely zero potential left to perform work relative to its surroundings.
Okay, that makes sense. It's the baseline. So we need some way, some function to measure how far our system is from that dead state, from that zero work potential. And this isn't just for pistons pushing air, right? We need something general for like shaft work from a turbine or even the theoretical work from a perfect heat engine.
Exactly. And that's where the non-flow availability function, just A, comes into play for closed systems. It's actually a really elegant combination of the key energy components all viewed relative to that dead state.
All right, let's see it. What's the function?
The availability A is defined as A equals U plus P naught V minus T naught S.
Okay, U plus P0 VGOS. Looks like internal energy, the environmental tax term, and something involving entropy. Can you break down what each part is doing there?
Sure. U is just the system's internal energy, the energy it possesses internally. Straightforward. Then P naught V. That's related to the work potential associated with the system's volume against the constant environmental pressure, P naught. It accounts for that displacement work potential.
Right, the environmental tax part we discussed. And the last term, minus T naught S, that smells like the second law making its entrance.
That's exactly it. The T naught S term is the critical piece here. It represents the energy that is inherently unavailable for conversion into work. It's the portion that, according to the second law, must be rejected as heat to the surroundings at temperature T naught during any process bringing the system to equilibrium. It's the mandatory heat rejection quantified.
So availability A is telling us,
Yeah.
here's the internal energy you have, U, plus the work potential related to displacing the environment, P naught V, minus the energy you absolutely cannot turn into work because you have to dump it as heat, T naught S.
Precisely. And now, here's the payoff. The reason this function is so powerful, The maximum useful work, WU max, that you can possibly get from a closed system changing from some initial state 1 to a final state 2 is
Mhm.
simply the decrease in availability. WU max equals A1 minus A2, or minus delta A.
Hold on. That seems almost too simple. You're saying we calculate A at the start, calculate A at the end, take the difference, and that's it. We don't need to worry about the exact path, the friction, the type of expansion, none of that messy intermediate stuff to find the theoretical maximum.
For the theoretical maximum useful work, yes. It gives us path independence for potential. It's the ultimate shortcut. We also often use the specific non-flow availability, little a, which is just availability per unit mass. So little a equals little u plus p naught little v minus t naught little s using specific properties.
Okay, this needs an example to really sink in. How does the shortcut play out in practice?
All right, let's imagine that piston cylinder setup again. We have air inside, starting at, say, a high pressure and temperature, that's state 1. It then expands and cools down to some final state 2. And the surroundings, the dead state, are just standard atmospheric conditions, T naught and P naught.
Okay, now the old-fashioned way, the textbook way, to find the maximum useful work for that entire process.
Ooh.
You'd have to meticulously calculate the work done during each tiny step of the expansion, figure out the heat transfer, account for the moving boundary work against P naught. It could get really complicated depending on the process path.
Exactly. You might have heat transfer involved, maybe work input or output through different means. You'd sum up all the useful work components along the entire, possibly complex, path. It could take pages of calculation. You'd track the work against the actual resisting force, maybe shaft work, maybe work via a reversible engine connected, and you'd eventually arrive at a single number for the net useful work.
But with availability.
With availability, you just need the properties, UVS, it's state 1 and state 2, and you need the dead state properties, T naught and P naught, which are constants. You calculate A1 plus P0V1 T0S1, you calculate A2 plus P0V2 T0S2. The maximum useful work is simply A1, A2.
And when engineers actually do this, compare the long path-dependent calculation with the simple availability difference.
The results for the theoretical maximum useful work match. They have to. It proves that this state function, availability, perfectly captures the maximum work potential without needing any information about how the system got from state 1 to state 2, assuming the process was reversible.
That's the aha moment then. Availability defines the ceiling. It tells you the absolute best you could possibly do in terms of useful work output between two states in a given environment.
Exactly. It sets the theoretical limit.
Okay, so we found the theoretical ceiling. Now let's talk about reality. The gap between that beautiful maximum number and what we actually get out of any real engine or process. That gap must represent waste, right?
It does, and it has a very important name. Irreversibility, usually denoted by I. Irreversibility is precisely the difference between the maximum possible useful work, the change in availability, and the actual useful work, WU actual U achieved. It represents a permanent loss of work potential, availability that has been destroyed forever, energy quality that's been degraded.
And how do we quantify how much availability was destroyed? How bad was the process? Does it relate back to entropy again?
It absolutely does. The irreversibility I generated during a process is directly proportional to the entropy generated during that process. Specifically, I equals T naught times delta S universe, or often simplified as T naught times the entropy generated within the system and surroundings.
Okay, let's make this concrete. Think about a turbine in a power plant.
Good example. An ideal, perfect turbine would expand the steam or gas isentropically, meaning constant entropy. That would give you the maximum possible work output, which would equal the change in flow availability. But a real turbine has friction, turbulence, maybe some heat loss. It's not isentropic. Entropy increases as the fluid flows through. Let's say it has an isentropic efficiency of maybe 85%.
Right, so that 85% efficient turbine produces less actual work, WT actual, than the ideal one. The theoretical maximum work it could have produced is given by the change in flow availability, minus delta in F. The actual work is lower.
Exactly, and the difference between that theoretical maximum and the actual work, WT actual, is the lost work due to irreversibilities. Now, if you separately calculate the irreversibility using T naught times the actual entropy change, S2, S1, across the real turbine,
Let me guess. It perfectly matches the lost work.
it perfectly matches the lost work. The irreversibility calculation, T naught arrays, quantifies the exact amount of availability that was destroyed by the friction and inefficiencies within that real turbine. Even though energy is conserved overall, first law, the potential to do work, second law, availability, has been demonstrably reduced.
So availability A measures the maximum work potential stored in the system relative to the dead state. How does the term Exergy fit in? I hear them used almost interchangeably sometimes.
They are fundamentally the same concept, measuring maximum useful work potential. The distinction is often subtle. Exergy B is sometimes defined specifically as the availability relative to the dead state itself, so B equals A minus A naught, where A naught is the availability at the dead state. Since A naught represents the baseline, often taken as zero potential, the change in exergy between two states gives you the same maximum useful work as the change in availability.
So for practical purposes in calculating maximum work, delta A and delta B tell you the same thing.
Pretty much, yes. They both quantify that maximum useful work potential. Exergy is perhaps more formally defined relative to that 0 point.
Got it. And you mentioned flow availability for the turbine. That's for open systems.
Right. For systems where mass is flowing across the boundaries, like turbines, compressors, pumps, nozzles, we use the steady flow availability function. If we neglect kinetic and potential energy changes, which is often reasonable, the specific flow availability, little a sub f, simplifies nicely. It becomes AF equals H minus T naught S, where H is the specific enthalpy.
HE zeros. So enthalpy replaces internal energy compared to the non-flow function. Makes sense for flow systems.
Oh, yeah.
Okay, let's tackle the process you mentioned earlier that really highlights why we need this thinking beyond the first law. The throttling valve. Ah, yes, the throttle. A deceptively simple device with profound implications. What does a throttle do? It just reduces pressure, usually across a valve or restriction. It's typically assumed to be adiabatic, no heat transfer, and does no work. So what does the first law, steady flow energy equation, tell us? If Q is 0 and W is 0, then enthalpy in must equal enthalpy out, H1 equals H2.
Right. Energy is conserved, enthalpy is constant. According to the first law, nothing really bad happened. The energy content per unit mass is the same.
But we intuitively know throttling is wasteful, right? You lose pressure without getting any work. It's a highly irreversible process due to the rapid uncontrolled expansion and internal fluid friction.
Okay, so if it's irreversible, entropy must increase. Entropy must increase. S2 has to be greater than S1 across the throttle, which means the irreversibility, I, which equals T naught times S2S1, must be a positive value. Availability has been destroyed. Even though H stayed constant, the flow availability, HT zeros, decreased because S went up.
Wow. So the first law sees nothing wrong. H1 equals H2. But the second law, through availability, clearly shows that the fluid's ability to do useful work has been permanently degraded just by passing through that valve.
That's the power of availability and irreversibility analysis. It reveals the hidden losses, the degradation of energy quality that the first law completely misses.
So wrapping this up, the core message for you, our listeners, especially engineers, seems to be this. Availability, or exergy, derived from the second law, is the essential tool. It's not just about conserving energy, first law. It's about preserving its quality, its ability to do work.
Exactly. The ultimate goal isn't just efficiency in the first law sense, output energy, input energy, but minimizing irreversibility. Every real process involves some irreversibility friction, heat transfer across a finite temperature difference, mixing, chemical reactions. These all destroy availability. Reducing them is the key to better real-world performance.
It seems like there's always this potential energy, this availability, that we could tap into if only our processes were perfect.
Which brings us to a final thought to chew on. Consider a standard internal combustion engine, like the Otto cycle. Thermodynamic analyses show that even after the expansion stroke, when the exhaust valve opens, there's still a significant amount of availability left in those hot exhaust gases being expelled.
Yeah, we try to capture some of that with turbochargers,
Yeah.
using the exhaust pressure and some heat.
Right, turbochargers recover some of the pressure-related and thermal availability. But to get all the remaining thermal availability out, you'd theoretically need something more complex. You'd need a bottoming cycle, a secondary heat engine designed specifically to take those hot exhaust gases and extract work as they cool all the way down towards the ambient temperature, T naught.
So the provocative question is, we know there's significant useful work potential being literally thrown out the exhaust pipe, beyond just the cost and complexity of adding a whole second engine cycle. What are the specific technological hurdles, maybe material limits, heat exchanger inefficiencies, or cycle integration challenges that prevent us from more effectively and widely implementing bottoming cycles to capture that wasted thermal availability from exhaust streams? That feels like a major frontier for pushing efficiency towards its theoretical limits.
A huge challenge indeed. Something for the next generation. Until the next equation design junkies, we are mechanical engineering made simple.